Yeah, Pradeep, are you able to see my screen and my voice is okay?
Yeah, yes, sir, it's okay. Yeah,
Okay, so we'll wait for a couple of minutes and then we'll
sure.
start.
Yeah, yeah.
Yeah, so we'll start now. Uh, First, I'll finish this boundary layer. One concept is remaining there. This integral solutions. So basically, we studied scaling analysis and this thing similarity solution for boundary layer, and then there is the third method which we could not finish last time because of the less time. But we can briefly look into it. Uh, so you might have seen like one direct formula is there. Uh, let's say uh, they call this as momentum integral method. So it is as the name suggests. In this method, you use integration over momentum conservation equations. So basically, Navier-Stokes equation. So uh, I'll there is a derivation. We'll do it quickly, and then we can look into the utility of this approach. Uh, this approach gives you a very you know very good closed form solutions, and also it is you'll see later that it is the, the 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 final result that we get can be used for any sorts of fluid flow, whether it is laminar, turbulent, or transitional flow, as long as you know the velocity profile of that flow. So let's get into that. So from the previous class, you may remember under some assumptions such as incompressible 2D steady fully developed flow uh, over a flat plate, we have x momentum equation. So I'm not writing all the assumptions because we are continuing from the last class. So you have the momentum equation as u del u by del x plus v del u by del y equal to uh, so basically you have this mu by rho term, which is kinematic viscosity, and then you have second order term which represents the uh, non sorry second order term which is associated with the viscous term. So you basically integrate this equation with respect to y. So if you do that, you get something like this, and this integration limit will be 0 to bound layer thickness plus the second term, same limits, del u by del y dy, and for the RHS also it will be same. So okay, so now you have three terms. uh, let's use some different color. So this is your first term, this is your second term, and this is your third term. So basically we manipulate
Sir,
these terms. Hello.
हेलो सर कुछ दिख नहीं रहा है स्क्रीन पे
Hello.
हेलो
Yeah, pardon, I could not hear you.
सर स्क्रीन पे कुछ दिख नहीं रहा है
Okay. uh, is it the problem from
अब
my
क्या
end?
पता सर और कोई हो उनसे पूछ लीजिए क्योंकि यार मेरा नेटवर्क प्रॉब्लम मुझे दिख नहीं रहा है
Is it same for Pradeep? Pradeep, are you also able to not see?
I'm able to see, sir. I'm able to see your screen.
Yeah, I am also see in my phone. I'm writing on my pad, but I have logged in through my phone also. So screen is visible here. Arnav, can you just
सर
recheck one?
आई rejoin
You rejoin, maybe that will solve the problem. Yeah, so moving on. uh, so what basically we do is, you know, this first term here itself, you can slightly manipulate it. The limit integration same. You can write this term as I am just rearranging the terms. So u square, if you take the derivative, it will be u del u by del x, and this 2 will be there. So that will go with the 1 by half. So moving on, we'll take the second term, which is 0 till boundary layer thickness u del u by del y dy. So if you see here, there are two terms. One is v, which is y directional velocity, and then you have a del u by del y, which is gradient of x directional velocity with respect to y. So you have to use integration chain rule, or by parts they call it. So if you do that, you get the first term remains as it is, the integration limits, and then in the second term you will end up with differentiation of the term which remains as it is in the first case, and this sort of equation. This is just a by parts integration by parts. Maybe you can look at the you can do it yourself and you can see the thing. It should be like this only. So now you can put the limits for the first term. So at delta, the v will be equal to v infinity and u will be equal to the u infinity. And then at 0, both of these terms, or at least u and no, both of them are 0. So u and v are 0. So uv also will be equal to 0. So that will be your first term. And the second term, here you can write it as minus del u by del x into u dy from momentum equation. So, sorry, continuity equation, mass balance. Since this is an incompressible flow, you have del u by del x plus del v by del y equal to 0. So you use and you replace the del v by del y term, and therefore you get v infinity, u infinity, and plus 0 by delta, 0 to delta, u del u by del x into dy. Correct, no? And if you see this term, I'll use 1 second laser pen, or maybe I can use highlighter. So this term, first term, and this term, they are same only, right? So, and they are on the same side. So when we add them, this will become 2 times, and therefore this half del u square by del y square, this one, it will be multiplied by 2. So that half will be gone with that. So if you do that, your left hand side of the equation modifies as not equation 1, maybe I can name it as equation 2. So basically it will become as v infinity, u infinity, and you will have 2 times 0 to delta half of del u square by del x del dy, and this half of will get cancelled because it's a constant, and you'll have only this del u square by del x dy term. Now the problem is this v infinity, we don't know what it is. So to eliminate that, what we can do, we have continuity equation, which is del u by del x plus del v by del y equal to 0. This is valid for 2D incompressible flows, right? So, yeah. Anybody asking anything? I think by mistake someone has unmuted. Second. Can you mute yourself? I'm not able to do it. Okay, thanks. Again, it's better. Okay. Yeah, so now I have muted the participant. I hope it stays that way. If you have any question, you can type it out. If you have a background noise, it's okay. So you integrate this also. So see, the name of the method is integral method, right? So you integrate everything. And I'll tell you why, because there is an interesting result at the end. So bear with me through this derivation. I'll do it fast so that it will not take a lot of time. So basically, you integrate this again with respect to y. And the right hand side anyway, it is 0. So it becomes 0 only, even if you integrate. So now if you look at this term, it will become v velocity from 0 to delta, which is nothing but v infinity, right? So now we got v infinity in some form. So now therefore we have v infinity as minus 0 to delta del u by del x dy. Now you put this in equation number, let's say 3. So therefore equation number 3 modifies as, you know, it will become minus u infinity 0 to delta del u by del x dy plus 0 to delta del u square del x into dy. Correct, no? Yeah. Maybe we'll put equal to sign here. Now, after this, there is one interesting mathematical identity which is called as Leibniz rule of integration. So that is used for differentiation under integral sign. So here everywhere you see integral sign is there, but inside all the differential terms are there. So to simplify that, we use Leibniz rule. One second. So basically, for differentiation under integral sign. So this is a standard rule that is used, and you know, it is given as d by dx. Let's say you have some limits of a to b, which are function of x, and you have some function f, which is function of two variables, and you integrate with respect to y, which we are doing here. So the Leibniz rule says you can write this term as sort of differentiation under integral sign, and then there will be two extra terms, because now basically what you are doing, you are taking the integral outside and differentiation inside, right? But if you do this manipulation, there will be additional two terms, and they will be like this, minus f of x ax into dA by dx. So this is the standard rule. You can find the proof for this on any website over internet. But the thing is, the thing that you should remember is, if you interchange or if you take the integral side inside the differentiation, you'll get these two additional terms. So that's it. If you can find these two terms, you can, take the differentiation and integration and, manipulate them. So now you can take, we have two terms, right? This term and this term. So you analyze each of them separately. What you do, first take, we will take the first term. So we have, a as 0, b as delta, and f, which is the function of x and y, is nothing but u of x. Right? This is valid for this term. I am not taking u infinity because it is anyway constant, so I am leaving it outside. So if you do that, what you get is, yeah, so in that case, apply this formula. So this formula is d by dx integration 0 to delta u dy is equal to 0 to delta del u by del x, because it is del f by del x here, into dy. I am just writing this equation in terms of these values, right? You can, try to understand that way. And then you have f of x into b. So basically u value at delta. So that will be nothing but u delta, u infinity, free stream velocity. Then you will have d delta by dx. And since a is 0, that term will not appear. So that will be basically 0. And now, and also for the second term, take a equal to 0, b equal to delta. They remain as it is, but now f changes. F becomes u square, because you have this term, right? So there is f is u square. So like that. And if you do the same thing, what you end up with is d by dx 0 to delta u square dy equal to 0 to delta. These limits will remain same. This will become del u square by del x into dy plus u infinity square into d delta by dx minus 0. Now here u infinity square comes because in bracket you have small u square. So this is there. Now what you do, you take these equations and you put them back in, let's say I call it as an equation number 4. So you put these in equation 4. So what you end up with is your LHS is nothing but minus u infinity remains as it is. The bracket term changes, it becomes d by dx 0 to delta u dy minus u infinity d delta by dx. This is your first term, which was u infinity into this integral, and then you have an additional term which is the u square term, and that becomes d by dx integral 0 to delta u square dy minus u infinity square d delta by dx. Okay, so now you further simplify these terms. So what happens, if you see, you have two differentiation terms, d by dx, and then you have two d delta by dx terms, right? So you can one second. Yeah. So if you see, you can further simplify this term as uh, minus u infinity d by dx 0 to delta u dy plus u infinity square d by dx, right? And it gets cancelled. This term and this term cancel each other. So basically, you only remain with yeah, you remain with minus u infinity, the first term d by dx 0 to delta u dy. This is only the first term, and then from second bracket you get uh, d by dx will be there 0 to delta u square dy. And now you can club these two terms together because integration is with respect to y and limit is 0 to delta for both the terms. And u infinity you take it inside because it is anyway constant. So if you do that, you end up with 0 to delta, and you have u square one term, and you'll have minus u infinity as the other term, right? So this will be your uh, one term. So this is your LHS, the final simplification of LHS. And let's take RHS. The simplification is simple for RHS of equation, I think it was 2. So if you do that, so basically what is your RHS there? RHS is right hand side. It was uh, the kinematic viscosity, we consider it as constant, and you had second order term here. Okay, so since the integration is with respect to y, you will end up with essentially first derivative, and the limits will be 0 to delta. And we know that at y equal to delta, del u by del y is equal to 0 because u approaches u infinity. So there is no gradient there, right? So therefore, uh, you have first term becomes 0. You have minus del u by del y at y equal to 0. So basically, you have minus kinematic viscosity del u by del y at y equal to 0. And therefore, then finally, combining LHS and RHS, we get, you have d by dx into 0 into integration. You have u square minus u infinity dy is equal to minus gamma del u by del y at y equal to 0. And this is a famous equation which is uh, okay. This del u by del y equal to 0, you know that tau is nothing but mu del u by del y, right, at y equal to 0. So if you use that manipulation, this becomes tau all by density. And this is a famous equation called as von Karman's momentum integral equation. So you may heard this term, you might have in some literature. And so the nice form for it is further simplified. What you do, you this side is simplified by dividing by u infinity square, and if you do the same for the RHS, uh, yeah, there will be minus sign here, so we have to do the reverse inside here. So it will be u by u infinity into 1 minus u by u infinity dy. I am just dividing both sides by u infinity square. And now, if you remember from our previous class, this is nothing but your, what do you call it? Momentum thickness, right? So this is nothing but momentum thickness. So typically in literature it is denoted by theta. So if you do that, you get tau wall by rho infinity square as d by dx of 0 to infinity into no, this term will go with theta, so it will be only theta. So this is your final solution equation, basically, not the solution. And keep in mind, this is valid only for flat plate. Okay, so if it is not a flat plate, we will have one additional term, and that will come because of the pressure gradient. Anyway, that is out of the scope for this course, but you should remember, valid for flat surface. I'm just noting it down here so that you remember it in future. Now, yeah, so sorry for this math, but this is what it is. And actually, since we are talking about fluid mechanics, there is this momentum integral solution for fluid mechanics. But if you study convective heat transfer later, somewhere in your other courses, there also, basically here we are studying a boundary layer, which is because of the, viscosity effects of the fluid. That is called as hydrodynamic boundary layer. But there is another type of boundary layer which is called as thermal boundary layer, and that happens when your plate is heated and the fluid flowing over it is at not same temperature as that of the plate. So there will be thermal boundary layer there, and exact similar procedure is there. So this momentum integral equation is also there in your convective heat transfer course also. So but the derivation is exactly more or less same. So if you come across that, you may check these two derivations, and they will be more or less same only. So anyway, that is also not part of this course, but I just thought, if I give you the analogy, maybe that will help you later. So now, you know, yeah. So now the important part, this equation is valid for laminar transitional and turbulent flow. So like any type of flow, it is valid because in the derivation, we have just come from the basic Navier-Stokes equation, simplified Navier-Stokes equation. But it is valid for all types of flows, but you must have velocity profile for that flow. So what I mean is, if you remember in the last class we derived, for laminar flow, this is just a recap of last class. For laminar flow with boundary conditions, boundary conditions which were at y equal to 0. Uh, 1 second. Yeah, at y equal to 0, u equal to 0. At y equal to delta, u equal to u infinity, and del u all by del u y by del y 0. And at y equal to 0, you have another boundary condition which was second derivative 0. So using these boundary conditions, we had arrived at the velocity distribution within the boundary layer, which was something like this. This is a very famous velocity profile. You should remember this uh, later also. And we had simplified it by assuming one uh, uh, dummy variable just for the sake of ease of writing. So now, if you know such velocity profile for your flow or your boundary layer or whatever it is, then you can use the von Karman equation, because this, if you see here, uh, here you need to put some velocity profile, then only you can solve it, otherwise you can't. So that is the only necessary condition. And since this is the famous equation for boundary layer uh, velocity profile, we will solve this equation for that, and we'll just see the results. So now, from the last class, do you remember the, what was the momentum thickness? Or if you don't, it's fine. We will try to do it today. So let's use it. So first of all, we need tau wall. So tau wall, as I said earlier, it is, since we are considering it as a Newtonian fluid, it is this expression, right, for tau wall. Now, from this velocity expression, uh, velocity profile, we have del u by del y will be equal to u infinity into 3 by 2 1 by delta minus 3 by 2, it will be y by delta square into 1 by delta cube. Just a differentiation of this. Let's say I put it as equation number 5. So if you differentiate equation number 5 with respect to y, you will get such expression. And if you put y equal to 0 in this expression, what you end up, the second term goes away. So what you end up with is 3u infinity by 2 delta. Therefore, your tau wall is nothing but mu into 3u infinity by 2 delta. So you have some expression on the tau wall side. Now come to the other side of the momentum equation, which is, so we have tau wall by rho u infinity square is nothing but d by dx of 0 to delta u by u infinity 1 minus u by u infinity dy. So this is what we derived so far. And we have some sort of expression for this. So that part is sorted. Now we need to solve this part. And I think we did it in the last class, but let me just have a quick look at it. Because here you get, I mean, if we had done it, no need to reinvent the wheel, right? So what did you get in the last class? 3 by 2, right? So yeah, theta we got as 39 by 280. So we have done this integration last time, and what we got is 39 by 280 into delta. So for now, I will assume some constant k into delta. This is constant, which is nothing but 39 by 280, because I don't want to write it everywhere. and it is approximately equal to this value. So now coming back to our main thing today. So what we have here is, again, uh, I'll write 1 by rho infinity square as it is. Tau wall is nothing but 3 mu u infinity divided by 2 by delta. So this is your LHS, and on RHS you will have d by dx of some constant into delta. So I can take this constant outside, right, because it is not a function of x. So this becomes your d del by dx, delta by dx. So now you can take this term on right hand side together. So what you end up with is del by d del x will be nothing but this 1 u infinity will get cancelled. So you will have 3 mu at the top, u infinity get cancelled, and at the bottom you will have 2k rho u infinity. Okay, so now this whole thing on the other side is nothing but a constant, right? So uh, it's just a constant because all other parameters are constant here. So therefore it becomes very easy to integrate. You can assume this again as some constant, let's say capital B. So we have d by dx is equal to capital B into dx. So you integrate on the both side. What you get, del square by 2 is bx plus c, some constant of integration, right? We know that at x equal to 0, delta is 0, right? I mean, we assume that at x equal to 0, the boundary layer thickness is 0. Strictly speaking, as I think mentioned in the last class also, at x equal to 0, it is a stagnation or singularity point, not a stagnation, it's a singularity point. So the correct term will be this. As we approach x close to 0, boundary layer thickness also approaches 0. You cannot say they are exactly at equal to 0. Maybe you can refer to the last class video. There I have explained it. So now with this boundary condition, what we get is c equal to 0 because delta and x all 0, so c is 0. So therefore you have uh, you know delta square equal to 2bx, correct now? And again I'll put back the value of 2b, b. So b was this value. So if you do that, you get 3 mu by k rho u infinity into x. And here what you can do is you can divide both sides by x square. So delta by x square becomes 3 mu. This remains as it is, and you'll get 1 by x over here. And if you see, if you rearrange the terms, let's say I'll keep 3 by k here as it is. You have mu rho u infinity into x. And we know that this ratio is very famous ratio, which is Reynolds number, and it is the inverse of that.
So actually two into three, I think should be two bx
Uh,
delta square is equal to two bx.
yeah, see, this was 2bx, right?
Yeah.
But b value already has 2 here.
Oh yeah, that's right.
So that 2 gets cancelled there. So now if you see, you get a simplified equation, which is nothing but delta by x will be uh, square root of 3 by k into this. And we know the value of k, right? K was something 0.139. So if you divide 3 by 0.139, 3 divided by 0.139, you get 21.58. And if you take the root of this number, you get 4.64. So therefore delta by x is 4.646 Reynolds number power, and this is the famous approximate solution for boundary layer. And the exact solution was given by Blasius, which we discussed in the last class, which is nothing but the the similarity solution method, which was developed by Blasius. So you get it was 4.9, but let's assume it as 5. So similar results we get, only the constant of the equation changes. So yeah, so the advantage of this momentum integral method is it's very easy, and you don't need to do any numerical method solution at all, and you get fairly correct values. And then there is one more thing, which is what we call as a skin friction coefficient. This is also called as a drag coefficient. Okay, drag friction coefficient, because they all are associated with something which is parallel to the flow direction. So it is defined as this: tau wall by half of rho u infinity square. And we know that tau wall, it has some form which is 3 mu infinity by 2 delta, and then again you divide it by half rho infinity square. So basically what you end up with is, if you do all the manipulation, we have just did that, you have to just put this delta, where it is. Yeah, so we have some form for delta, right? So you need to put this equation in this ratio, and if you solve it, you should get, I'm skipping that part, but it's straightforward calculus. I mean, you end up with something like root 3k into rex power minus 1 by 2, and we have this k value, right, which is 0.139 here. If you put that value in this thing and solve it, you get 0.646 into rex power minus 1 by 2. So this is your CF. Yeah, this is CF formula. And this exact solution by...
Sorry to ask this question, but where from this K is coming actually? This K is
yeah, so this K, right?
yeah.
This K, actually it came from the last class. So
All
in
right, yeah,
last class
yeah,
we
okay.
solved for the displacement thickness, right? So we
Yeah,
get...
right, right.
Okay, okay. So there, this K, don't worry about it, it's just a number, and if you just put the value, you get the because I don't want to write 0.139 everywhere, so that's why I'm just putting K here. Anyway, so if you see the exact solution given by Blasius for CF, and this is a local skin friction coefficient. Okay, it's not the overall. Overall, if you have to integrate over the length. So Blasius gave the value as 0.664. So momentum integral also gives fairly close, solutions. So that was the point. Anyway, so we solved it for a laminar flow, and as I said at the beginning of this derivation, that it is valid for turbulent flow as well. I'll not. Let me just think about it. I have that thing in mind because laminar solution is available at most of the standard books, but for turbulent flow, uh, turbulent flow over a flat plate. See, turbulent flow is not a nice flow to solve on the pen and paper, because basically turbulent flows are solved using statistics, because you can't have a smooth laminar flow. In turbulent, you have all sorts of eddies, and mixing is very predominant. So from the point of view of mixing or heat transfer, turbulent is good. But from the point of view of teaching, the turbulent flow is bad. You cannot have all this, sophisticated formulas for it. But fortunately, this one Karman momentum equation is valid for turbulent flow as long as we have some idea about the velocity profile. So from experimental observations, it is well established that for a flat plate flow and turbulent flow regime, the velocity profile is of the order of it is something like y by delta raised to the power 1 by 7. So you can ask me from where did you get this 1 by 7 power. So that is an experimental observation. There is no derivation for it. And similarly, for wall shear stress in laminar flow, we have a very nice formula which is mu du del u by del y at y equal to 0. But for Reynolds number, for turbulent flow, you don't have such nice formula. You have a
So in case of U infinity, can you write only U? Is possible, or it will be wrong actually.
no, you can write u. This u infinity is essentially to denote that it is very far velocity out of the boundary layer. You can write capital U as long as you know what it is. And now if I change it now, the whole thing I have to change. So
No problem.
yeah, but you can write U. There is no problem there as long as you know that it's a free stream velocity and it's a constant for our analysis. And yeah, coming back to the wall shear stress, it is also not empirically, experimentally derived relation for wall shear stress, which is given as uh, one second. Yeah, so it is given as mu rho u infinity into delta power 1 by 4. So these expressions, they are experimentally derived. And then again, you have to repeat the same process because we have, one Karman momentum integral equation as, which was tau wall by rho infinity square was d by dx of 0 to delta u by u infinity 1 minus u by u infinity into dy. Correct, no? So yeah, so again, now you have this u by u infinity velocity profile and you have wall shear stress profile as well. So if you plug these values in this, okay, I can do that. Let me just see. Yeah, so basically, one second. This is, yeah, so you can do this exercise. I'll give you the solution. Maybe you can do it on your own to get the exact things. But let's keep this term as it is. We'll solve the LHS because that is easier to solve, and that is also the thing that takes time. So u by u infinity will be y by delta 1 by 7 1 minus y by delta power 1 by 7 into dy. Just putting the value or the expression inside. So now if you multiply both the terms, what you end up with is y by delta power 1 by 7 minus y by delta power 2 by 7 into dy. Correct, no? And now if you integrate them, so what basically happens, see this delta is only function of x. So delta comes out of the integration, and 1 second. Y by delta 7 plus. Yeah, so this will become d by dx 0 by delta, or maybe I can remove the integration sign. We'll do the integration only. So 1 by delta power 1 by 7, because this is not a function of y, and y power 1 by 7 integration will be y raised to 1 by 7 plus 1 divided by 1 by 7 plus 1. Okay, and minus 1 by delta power 2 by 7. This is a constant with respect to y. It becomes 2 by 7 plus 1 divided by 2 by 7 plus 1, and the integration limit is between 0 to delta. So now if you see, if you put delta equal to 0, the whole thing goes away, because y equal to 0, whole thing goes away. When you put y equal to delta, what ends up happening is this 1 by delta power 1 by 7 gets cancelled with 1 delta. So you will end up with let's say delta into this will be 8 by 7 minus 1 delta will remain here also, and at the bottom it will be 9 by 7. So that 7 will go at the top, and this will be 1 by 8 minus 1 by 9. So that will be 1 by 72. So that will be 7 by 72 into d by dx into delta. Okay, so now what you do, you put the tau wall expression also here. So we have this expression, right? Experimentally determined equation, and you can put it here. So if you do that, what ends up happening is 0.0225 mu by rho u infinity into delta power 1 by 4 becomes 7 by 72 into d delta by dx. Yeah, correct. So now you do one thing. These are constants. They won't change. That mu by rho infinity is also constant. The only variable is delta here and d by dx here. So you take these two terms together. So now if you do that, what happens is so something like this will happen. So 0.0225 remains as it is. This 72 by 7 will come here. You will have one term which will be mu by rho u infinity power 1 by 4, and this will be have dx here, and you will have delta power 1 by 4 minus sign will be there. No, it will be plus because it is coming there into d delta. And now you do the integration on the both sides. So what will happen is you will have delta power 5 by 4 divided by 5 by 4 into this whole equation, which will be 0.0225 into 72 by 7 into mu by rho u infinity power 1 by 4 into x plus c. And again, as x tends to 0, delta tends to 0, which gives c equal to 0. And therefore, if you solve it, what ends up happening is okay, I'll do this multiplication myself. 0.0225 into 72 divided by 7. So this constant is 0.23 4. Okay. So you have 4 by 5 into delta power 5 by 4 equal to 0.2314 into, this is also constant only, but I am not uh, doing anything to it, just to, later we'll manipulate it. So this is the reduced form of this equation. Now what you do, yeah, so basically we have to convert this term, this term into some form of Reynolds number. So to do that, what we can do is we can write this as 0.2314 into mu by rho infinity into x power 1 by 4, and then we have to multiply with x power 1 by 4, right? Because we divided by x power 1 by 4, and 1 x which was originally there, it will remain as it is. This is just a manipulation to get a nice form of equation. And if you see, now this constant remains as it is, but this becomes what it becomes? It becomes 1 second, 1 by 4, correct? We divide by so this will become power 5. Okay, yeah. So this becomes Reynolds number power, local Reynolds number power minus 1 by 4, right? Because it's an inverse of Reynolds number. Then you will have x power 5 by 4 because these two gets added, powers get added. And now you can do one more thing. You can put this delta by x because both of them have power 5 by 4 together. And this 0.8 will be, going there. So it will become 5 by 4. So this value into 5 divided by 4, it becomes 0.289 into Reynolds number minus 1 by 4. Okay, and then what you do, you take the basically you do this delta by x 0.289 power 4 by 5, and this will become Reynolds number minus 1 by 5. This is just a manipulation of powers, so the constant will change, that's it. And if you do that, what ends up happening is you get the constant which is 0.31371. So you get this very well known expression for turbulent flow. This is a very well known expression and very widely used expression for flat plate turbulent flow, flat plate turbulent flow. So this is there. Yeah. And similarly, you can solve for, this drag coefficient, which is
But
again.
sir, in the question, suppose they don't give any turbulent and laminar, which one will follow? This one or the other one? That 1.5, that 1.9, yeah, 5 or something.
See, if they don't mention which type of flow it is, first of all, the question is wrong. But I understand in some exams such things happen. Most likely, you assume it as laminar because 95% or even more than that mentioned, better to assume laminar because otherwise, turbulent flow, you may not remember the equations and all because it's not that commonly taught. So if you don't have any information, go with the laminar flow. Okay, and if you solve for this, CF, which is nothing but tau wall by half rho infinity square. So if you do that, you basically end up with, I'm not going solving there because it's similar to what we did earlier. So you end up with this expression, and here this is also very well known equation for turbulent flow. Yeah, I mean, I'm skipping the algebra for this, but it is similar to what we did earlier, right? So here, you put tau wall by half rho infinity square, and you just solve it. So the power of Reynolds number remains same for delta by x and CFX. Only this constant changes, and this is the local skin friction coefficient. So yeah, so with this I can say that the boundary layers theory is finished, and now we can move on to the next part, which is open channel flow. To be honest with you, since I am from a mechanical engineering background, open channel flow is not in our syllabus for GATE or engineering services or even civil services. Open channel flow is not for mechanical engineering students anymore. I think it was there earlier, but not now. So at least since when I was preparing, it's not there. For civil engineers, it's very important topic, and that's why I think it is covered in this NPTEL course as well. So the point that I'm trying to convey is, for the last 11 lectures, I did not prepare much because I knew most of the things. I just revised before lectures, on the weekends. But for this open channel flow topic, I have to really prepare myself because it was new topic for me as well. So anyway, I have seen the NPTEL course videos also for this, which were uploaded by professor, as well as the assignment questions. So I have understood some important concepts basically there. Uh, so, and I have gone through this reference of FM White, Frank White book, and most of the things that I'll discuss here after this point, they are mostly from this book only, and they more or less will cover all the topics that are in the scope of this uh, syllabus of this subject. So let's go into that. So yeah, first of all, as the name suggests, open channel flow, that means it will be open. At least one surface, I mean not at least, one surface will be open to the atmosphere. So it's a tricky thing. Okay, so for example, I can make one question, maybe not a MCQ, but interview question. So see, if I say, let's say if I have a rectangular canal or some flow like this, why is it giving me square? I don't know what square. Anyway, so let's say if I have something like this, so this is clearly an open channel flow. So you have this solid boundaries, and you will have some free surface, and there will be some fluid flowing, and this is an open channel flow. But at the same time, I can, like, maybe some students like me may get confused if I give you some flow like this. So let's say it is a rectangular channel, but it is not fully filled. So it is, let's say, filled only till half of the height, and 1 second, and let's say this is your flow domain. So, and only half of this is liquid. And even in the case of circular pipe flow that we studied earlier, there can be a situation where the pipe is not fully filled, it is only half filled. So the point that I'm trying to convey here is, open channel flow does not necessarily mean there will be a flow which will be open and you can see the flow. There are closed conduits such as rectangular or circular or any other shape of pipes. If it is not fully filled and if the other side is open to the atmospheric pressure or any other pressure, typically we consider atmospheric pressures because most practical applications will have that, but that is also open channel flow. So all these examples are nothing but the open channel flow examples. I just wanted to clarify this right off the bat because some students may have confusion there. I mean, at least some students like me. Anyway, so next, in open channel flow, uh, there are important forces which governs the flow, which are gravity forces and uh, frictional forces. Sorry, yeah, gravity force and inertia force. I think. 1 second, let me just, because in pipe flow we know uh, the flow is governed by the pressure gradient because otherwise flow will not take place. So then there becomes frictional force and this pressure gradient force. They will become the dominant forces. But in case of open channel flow, gravity force and the frictional force, they are the dominant forces governing the uh, open channel flow. So here important difference is flow is governed by gravity and friction, not pressure gradient. So this is an important distinction that should be understood. And yeah, then typically in this course we are studying one-dimensional uniform open channel flows and mostly through the straight channels. They may have some slope or some flat things, but mostly we are studying 1D incompressible straight channel open flows. So because typically speaking, these open channel flows are highly turbulent, and they since it's a turbulent regime, you cannot have an 1D approximation. In any case, in open channel flow, we have to do 3D simulation, but that is not possible to do it on the pen and paper with the pen and paper. So for the sake of this course, we are considering it as a 1D flow, and yeah, that is the assumption for for like if you want to study more, I would advise you to refer to the chapter on open channel flow in the Frankham FM White book. Uh, whatever I'm trying to tell you here is from that book only. And one more important thing here to remember is, uh, yeah, since we don't consider, pressure gradient as an important parameter, we, approximate this mechanical energy conservation equation, that Bernoulli equation, but not, uh, you know, Bernoulli equation plus frictional losses, and that will be your general mechanical energy conservation equation. That is also valid here. But important thing is this Reynolds number that we calculate. Uh, Here we use hydraulic radius instead of, I mean, the characteristic length is hydraulic radius here, and the important distinction is it is only cross-sectional area by wetted perimeter, whereas hydraulic diameter is nothing but 4 times cross-sectional area by perimeter from our previous discussion, and this is the wetted perimeter. So I think in the very initial classes only I had told that this wetted perimeter concept becomes important for open channel flows. We will see some examples, but I just wanted to clarify this, and therefore this is 4 times the hydraulic radius. In closed pipe flow, or in a closed, I mean I'm using it in the sense that it is a fully filled pipe. We had the hydraulic diameter which was 2 times the radius, 2 times the hydraulic radius. But in case of open channel flows, it is 4 times. So this is also very highly commonly asked, MCQ type of question from open channel flows, because typically students remember it as twice because radius is or the diameter is double the radius, right? That is typically okay, but for open channel flows it is 4 times because of the definition. Then yeah, uh, yeah, as I said, since the flow is governed by gravity and friction, your Froude number is the important parameter here. So as in the initial classes only we discussed this. So Froude number is nothing but the velocity, average flow velocity divided by the uh, root, under root gy. This under root gy is typically called as surface wave speed, and this y is nothing but the depth of your uh, uh, open channel. And there is a classification based on this. Many MCQs are asked based on this only. So FR can take 3 values. Sorry, it can take 3 values. It can be less than 1, which is called as subcritical flow. It can be equal to 1, which is critical flow, and it will be greater than 1. It is supercritical. Since we have not covered it in this course, but most of the things that most of the derivations or other things that we study here, concepts like hydraulic jump, etc., they are more or less analogous to the concepts in the shock waves. Compressible flow is another domain, another subject altogether of fluid mechanics. But for this course, we majorly studied incompressible flows. But in reality, many flows are compressible as well, and compressible flows are studied separately. And then there is, in the compressible flow course, you will encounter something called as shock waves. So similar thing happens in the open channel flow as well. So if any one of you know how to analyze compressible flows, you can draw the analogy. If you don't, it's okay. Maybe in future when you study the compressible flows, you can just look back at your this class notes, and you can it will be easy to understand there. Anyway, so yeah, then maybe we can take some questions over this. 1 second. Like straightforward questions can be asked from here. Okay. Uh, Maybe I can take one question, and we can go to the next important thing. For example, I can frame one here itself. Let's say uh, 1 second. Yeah. Yeah. So let's say for an open channel, uh, okay, I can give you one figure that will be good only. Okay, it is giving me rectangle every time. Anyway, so I will make it as. So this is your open channel flow, and this dimension, let's say, is 1 meter. this dimension is, let's say, 10 meters, and average flow velocity across the channel is, let's say, 2 meters per second. And yeah, I think I can ask you what is the Reynolds number for this flow, and what type of flow it is. So basically, the things that we covered so far can be asked in this sort of fashion. So we can calculate the hydraulic radius, which will be nothing but the cross-sectional area divided by wetted perimeter. Oh, this is P. And cross-sectional area will be 1 into 10 meter square divided by wetted perimeter will be 1 plus 10 plus 1. Okay. So this is nothing but 10 by 12. So 5 by 6. So 5 divided by 6, it will be 0.833 meters. And therefore the Reynolds number will be rho v hydraulic radius by mu. For water, the density will be, let's say I give you the density as 10 to the power 3 kg per meter cube, since it's a water. And dynamic viscosity for water, let me just check it once. 1 second. I think it is 10 to the power minus 3, but viscosity of water.
Sir, 0.074 Newton second per meter square.
Yeah, so roughly we can take it as 10 to the power minus 3 Pascal second. Okay. Yeah. I mean, exact values, obviously you know better than me, but I'm going with the Google here. So it is giving me as 10 to the power minus 3 in standard units, which is Pascal seconds. So if you do that, you will get Reynolds number as 10 to the power 3. Velocity is 2 meters per second. This is 0.833 divided by 10 to the power minus 3. So I mean, exact value you can calculate, but from here itself it looks like 1.66 into 10 to the power 6. I hope it's correct. Yeah, I think it's correct. So this is your Reynolds number, and then you can calculate the Froude number, which is average uniform flow velocity divided by the surface wave speed. And here the velocity is 2. Let's take it as 9.81, and the flow depth is 1 meter. So if you divide, let's say 9.81, if you take the square root, it is 2 by 3.132, and it will be 0.64. So since this is less than 1, this is subcritical flow. Okay. So similar type of questions can be asked. Maybe I can take it some question later, but let's move on. So this is about the initial things. Yeah, then there is, for pressure drop or frictional head loss due to sorry, not pressure drop, frictional head loss, pressure head loss, whatever they want to call, but head loss due to friction, if you want to calculate, there are two ways in in case of open channel flows. first is called as Chezy formula, and another I think Manis coefficient. So both of them are used, but I mean, you know, if you want, I can give you the thing, but I mean, I am reluctant because this was not discussed in the class. But in assignment, there was one question on this. I remember I saw it. So anyway, I'll give you the equation. Maybe you can use it later. So 1 second. This yeah. So for frictional head loss, you have this Chezy formula, which gives you the flow rate as uh, area into velocity. And for velocity, actually they give the formula, but I'm writing in terms of flow velocity or flow rate. So basically, it is given as 8g by frictional Darcy's friction factor raised to power half into hydraulic radius power half and slope of the channel power half. So S is the slope of the channel, and yeah, so basically you calculate it as tan theta if required. Otherwise, it is generally given. And this guy is also a constant, so they typically assume it as constant. And you can write as some constant into area into hydraulic radius power 1 by 2 and slope power 1 by 2. This constant, there is one table and you can get it from there. And then you can have an average frictional stress or shear stress, which is nothing but rho g hydraulic radius into the slope. So these formulas are given by Chezy. The only unknown that is required in these is the c, which is constant, and that also you can calculate if you have some idea about the f, the Darcy's friction factor. Otherwise, you can use some table. The c is called as Chezy coefficient also. So if you have direct access of some correlation for Chezy coefficient, you can directly use that also. Otherwise, you can calculate it from this Darcy-Weisbach friction factor. Okay, so this is one method, and yeah, let me see if we can have one problem. Yeah, so we can take a simple problem, which is again, I can copy it from here. Same, you have a rectangular flow channel, let's say. Okay. So yes, let's say we'll take same dimensions, doesn't matter. The slope of the channel is 2 degrees. I mean, you will not have large slope values, okay, because these are practical canals and all, so they will have less values for the angles of slope. And the friction factor is is 0.22. It is given in the question. Dimensions are also given. Estimate the uniform flow rate using Chezy's formula. So we can use the relation. So here we can calculate C using 8G by F power half. So this will be 8 into 9.81 divided by 0.22, square root of that. Yeah, I don't have the value with me, but 1 second, I can calculate. So this is 8 into 9.81 divided by 0.22 and square root of it, right? So it is nothing but 18.887, and it will have the units of square root of meter per second square. So it will have the unit of like this. This is not a dimensionless number. It will have some unit. So keep that in mind. Then you can calculate the area, which will be 1 into 10, so 10 meters square. You can calculate hydraulic radius, which will be A by P, and I think we calculated it because the dimensions are same. So hydraulic radius will again come out to be 10 by 12, which is 0.833 meters, and the slope is tan theta, so tan of 2 degrees, and that will be equal to 1 second, tan okay, yeah, so I will put tan of 2 degree. It will be very small value, so it comes out to be 0.0349, and now you can use the Chassis formula to calculate. So you have some constant area, hydraulic radius raised to half, and slope raised to half. So you can put all this value. 887, area is 10.833 square root 0.035 square root. Therefore, okay, I'll do that. So this into 10 into 18.887 into okay, 1 second. Okay, so this is 35.929 294 into square root of 0.833. So 0.833 square root into 35.294. Yeah, so you will have your final answer as 32.212 meter cube per second. So now in some questions they will not ask you in meter cube per second, maybe they'll ask you in liters per second or cubic feet or whatever. Those manipulations you can do, it should not be a problem. So this is one method to do it, and then there is a second method, which is Manning's correlation. So basically it is also on the same lines, but here he replaced this constant C with some other constant, which will be again it depends on what type of fluid, what type of surface roughness it has in the channel, etc, etc. And here this constant is replaced, so basically you get Q as some constant N into area into hydraulic radius power 2 by 3 into s power 1 by 2. So here this power changes and the constant is some 1 by n. So this n value also there is a table from experiments, and for different type of surface roughnesses and different type of materials for the channel surface, Manning has given different n values, and using those you can calculate the flow rate. Okay, so we can take one question. Yeah, 1 second. Okay, so yeah, I can again consider the same flow channel. Yeah, I mean, instead of some numerical question, I can have another question also. So okay, I can frame a question like this. If in a rectangular cross-sectional open channel flow, width is 3 times the flow depth. Okay. Or instead of that, I can, I can simplify it. Let's say in a rectangular cross-sectional open channel flow, if width is if width of the channel is doubled, let's say, you can put any number here, what will be the change in flow rate through the channel, assuming other parameters same. Okay. So basically what I'm trying to ask is for a channel, if width is increased, another type of question can be for the channel, if the height is depth or the height of the flow is doubled or halved, maybe I can say if the slope is changed. So what I'm trying to say is using this equation, many other type of 1 second, many type of gate type of questions can be framed. Array. So let's say this question only. So we know, see, if slope is constant, if the channel material as well as the roughness is constant, this n and s will not change with your channel width change. So the q will be proportional to flow area and the hydraulic radius power 2 by 3. Correct. Now let's say you had channel like this, and let's denote the width by b and height by commonly in this type of parlance, y is used here. So your area is nothing but by, and hydraulic radius is nothing but area divided by weighted perimeter. So this will be by divided by b plus 2y, and you can put it there. So therefore q is proportional to the by into rh power 2 by 3, right? So by b plus 2y 2 by 3, correct? Here we can make one. Okay, so now the question says, so now if you know, the question says if you increase this thing, what do you say? Yeah, here some additional information is required, otherwise you can't get a straight answer. Okay, we'll make it a one variable problem. Let's say, and assume b so the width of the channel is 3 times your depth of the channel, and that is initially. So before increasing the width of the channel, your depth was 1/3 of the width. So basically that will simplify this problem. So if you put b equal to 3y, what you end up getting is b equal to 3y, and we want everything in terms of width of the channel, right? Because that is what is asked in the question. Yeah, so I can replace y with b by 3, so this will become b square by 3. This will be b square by 3, and here your y is b by 3, so 2b by 3 plus, so 5b by 3 power 2 by 3. So your q is nothing but proportional to the what will it be? This 3 will get cancelled, and 1b will get cancelled. So this becomes 1 by 3 will be there, 1 by 3, and from here 1 by 5 power 2 by 3 will come out, and there will be b square and b power 2 by 3. So that will be 2 plus 2 by 3, that is nothing but 8 by 3. So basically q is nothing but proportional to the 8 power 3, 8 by 3 power to the channel width. So like that. So if now let's say if b increases to 2b, q will increase by the factor of 2 to the power 8 by 3. And yeah, you can calculate this value using calculator. So like that. So my point here was there are some variables which determine the q value, right? So I can change one variable and ask you what will be the effect of that variable on the flow rate, and same thing I can ask in the Chezy coefficient also. So you get my point, I think. So like that. Yeah, so now these two are done. Yeah, and one more thing is that you should remember is, in case of open channel flow, if you know the depth, you can easily calculate the what you say flow rate. But if you know the flow rate, it is not straightforward that you can calculate the depth. One second. Wait. Charging is over. 1 second. I think there is some problem with my internet. 1 second. So yeah, so as I was saying, you can calculate this thing, flow rate, when your channel depth is known. But if channel depth is not known, calculating the flow rate is, when the flow rate is known and calculating channel depth from it is not straightforward. Sometimes you may have to do the iterative methods you may have to resort to. But let's not go there because, not required for us. I'm just giving you the hint here. Then moving on, yeah. So there is something called as efficiency of, for a particular flow channel. They define some efficiency, so they call it as an efficient channel. So what efficient channel means is, you should have, for a given cross-sectional area, you should have maximum hydraulic radius and minimum weighted perimeter. So I mean, basically they want minimum pressure loss due to the friction and maximum flow rate. So maximum flow rate will happen if you have, uh, maximum hydraulic depth for a given flow area, and minimum weighted perimeter will result in the minimum frictional loss, like that. So I mean, there is no, fixed formula. You can have, let's say, for a particular channel, let's say if it is a rectangle, if it's a trapezoidal, if it's a circular, semicircular, for all the channels, there is no common formula. You have to do the maths. For example, okay, we'll take one. Efficient flow channel. They define it as efficient flow channel, and that is nothing but which gives minimum frictional loss. So for that you need to have minimum weighted perimeter plus maximum flow rate. That means you should have maximum hydraulic radius, and for all of this you keep for given cross-sectional area. So you keep area as a constant and you try to maximize the RH value and minimize the weighted perimeter value. So typically we are using P symbol for weighted perimeter. So this is the definition of efficient flow channel. So yeah, so basically there is a general derivation here which can be extended to trapezoidal and later to the rectangular channels. So we have a symmetric trapezoidal open flow channel as shown here, and you will have this free surface here, and the bottom width is given as small b, the height is given as y, and this angle is given as theta. So it's a symmetric thing. So theta will be on the same both sides. So using trigonometry, if you let me use some other color for this. So using trigonometry, we can calculate this length will be nothing but y into cot theta. So let's put beta into y. Assume beta is a constant which is cot theta. This will solve our make our problem solving easy, or the equations smaller basically. So now what is your cross sectional area here? It will be by plus one rectangle will have area half beta y into y, and similar the symmetrical area the other guy will have same. You understood, right? This is y, so half into y into beta y, and the other triangle also that. So effectively we get by plus beta y square. And what is your weighted perimeter? It is nothing but, yeah, so now we have to calculate this this length also, right? Because this is your weighted perimeter. What am I saying? I'm talking about this length. Why am I changing the color here? I don't know. Yeah, so this also we need, right? Because this will contribute to your weighted perimeter. Let's say W. So your weighted perimeter will be nothing but B plus 2W. Now question is, what is W? So again we have to go back to trigonometry, and from figure we have a right angle triangle, this is y, this is beta y, and this is W. So we know that W square will be y square plus beta square into y square. Therefore W will be y into square root of 1 plus beta square. This is from the trigonometry. Now you can put it in the P formula. So this will become P into 2y 1 plus beta square root. Okay. Yeah, so now to get, so the objective here is we want to minimize P for constant area. So what is done is, and here beta is also constant. We are not changing the trapezoidal angle. So what they do is they take derivative of dp with respect to y and equate it to 0. Okay. One second. Now, if you do this, what will be the dp by? Yeah. Before that, we have to do one thing, right? Because uh, we have not correlated p with respect to area. So now we have equation 1 for area, equation 2 for perimeter. So now you combine them and eliminate some parameter to get the perimeter in terms of area. And if you solve, I'm skipping a few steps here, you will get equation like this. It's not that difficult. You can, get it easily. So now they do dp by dy equal to 0. Here a they assume as constant, beta is constant, so only variable is y, and you need to take the derivative with respect to y. And when you equate it to 0, I'm skipping some calculations because it will take a lot of time, and that is not important also. What we get is solution is perimeter, minimum perimeter will be 4y into 1 plus beta square root minus 2 beta y, and hydraulic radius we get as y by 2, and area we get as y square into 2 1 plus beta square minus beta. So I mean I have skipped the derivation here, but otherwise it will take a lot of time. It's not that difficult also. So important thing to note here is note whether it's a trapezoidal thing or what, for like for any theta your RH will be y by 2. Basically RH is not a function of theta. So whether it's a trapezoidal or rectangular channel, you will have for efficient cross sectional your hydraulic radius should be half of the depth. That is one important MCQ question asked in many places. And you simplify this for rectangular cross sectional area flow area channel. So see, for rectangle there will be no theta. I mean there will be vertical walls and theta will be 90, and cot 90 is I think 0, 1 by infinity. So we assume it as 0. So this beta will be 0 for rectangular channel.
So what is that? This RH is a function of theta. Want to say
No,
this?
RH is not a function of theta.
Or not a function of theta.
Yeah, because in RH formula you don't get any beta term, na? In perimeter and area you have this beta terms, but for RH you have only y. So RH is only function of depth, and it will be half for efficient channel. So now the important part, because mostly they talk about rectangular channels. So in rectangular channel your theta becomes 90, therefore beta becomes 0, and you will have RH will be remain as y by 2 because it is not a function of theta, but your perimeter will become 4 times y, and area will become 2 times y square. So basically for an efficient rectangular channel, and this is possible, I mean not only two equations, to satisfy all 3 boundary conditions or 3 necessary conditions are not possible, they are satisfied. These conditions are satisfied when your flow depth is half of your channel width, which is b by 2. Okay, so basically you will have some channel like this, let's say certain rectangular channel, and this will be your flow depth. So when your channel width becomes 2 times your channel depth, then your rectangular cross-sectional area becomes efficient. I mean that will be the best efficient cross-sectional area. You will have maximum flow rate and minimum frictional loss due to the friction. So that is there. I hope it is clear. This is very important finding. Okay, this is asked in many competitive exams. And yeah, and one more question. I am again skipping math here. They ask for a trapezoidal channel. What is the best value for beta? So basically they are asking at what angle theta you will have maximum flow rate. So for that, what you do, you equate derivative of perimeter expression with respect to beta to 0 and get the value. If you do that, here, area and y will be constant because only beta we are changing. So basically what you get is some condition like this. So, and then if you solve this further, you get beta as 1 by root 3. And this is nothing but cot theta, right? So cot theta is 1 by root 3 for theta of 60 degrees. So this is also one important question asked in many competitive exams. So basically when your trapezoidal channel is nothing but a half hexagon, then you will have what you call best or the maximum flow rate for minimum pressure drop or the efficient trapezoidal channel. That is there. You can try for other different channel geometries and you can get the expression like this, but rectangular channel and trapezoidal channel are common. For circular channel also there is such a derivation. I'm skipping it here.
So can you repeat what did you say in the last one? This difference between these trapezoidal and rectangular.
So yeah, so basically for beta value of 1 by root 3, you get the minimum perimeter. So that is the angle theta equal to 60 degrees. So if you see this image of the channel, which is highlighted here. So here, if you put theta as 60 degrees Celsius, this part, it will become like a hexagon, half bottom of the hexagon. Can you mute yourself? Someone's noise is coming in the background. Okay, thank you. So, did you understand, Pradeep?
Yes, yeah.
Okay.
Excuse me, sir. Excuse me.
Yeah. Tell me.
Efficient flow rate, which channel is the best, no?
Pardon?
For efficient flow rate in an open channel, the V channel is no among trapezoidal or rectangle.
That
Channel.
I can't comment like this. I have to check because I have not looked into the triangle one.
In a triangle, this perimeter, weighted perimeter is less.
Yeah, but
Triangle when compared to trapezoidal.
no, but you have to keep the area constant, right? So
Yeah,
if
throughout the channel, the area is constant. But this V section.
agreed. I understand what you're trying to say, but my point is, I mean, you may be correct. I have not seen the triangle channel derivation, but what I'm trying to say is, when you make this b equal to 0, basically in triangle.
Just for outlook, just for outlook, just imagination. That's all.
Yeah, I agree with you. It makes intuitionally sense to have a triangular channel, but what I'm trying to say here is maybe I can make my point.
Okay.
1 second. So let's say you had such a trapezoidal channel, right? And what your intuition is saying is, if you make this smaller and smaller, and eventually if you reach some triangular wedge shape like this, it may have lesser weighted perimeter, right?
Correct.
It can, but you at the same time you must keep in mind that the flow rate in the both channels we need to have as same. So what if it is q1 here, it should be same, and assuming the velocity doesn't change, what it means is your cross sectional area should be same in both cases. So now here the cross sectional area was
same. Only cross section is same. Only the depth increases.
So depth. So now, so see, there will be some critical value for depth, right? For which both the cross-sectional area will be same, na? So,
Correct.
so in that case, the triangle channel is better. But if you increase the y value, I mean, for this like certain y, if you fill it up to that level or even below that, this channel is better. Triangle is better. But you know, you have to see whether it makes sense or not. Maybe, I mean, we are running out of time, but
Construction cost also reduces.
yeah, construction cost is, I mean, practically speaking, though it is better. But again, see, uh, I mean, if we are talking about practical things like construction costs, etc., there is something called a sedimentation also, right? So for triangle, I think it will be more disadvantageous if some sediments and all, because they can easily get caught in between the wedges. Whereas for trapezoidal, they may flow along. So all other factors we have to consider, but assuming those things are not important, I agree what you are saying, but we have to do some calculations to get this y value, which will be the depth for that channel.
Okay, sir. Thank you.
Okay. So moving on, yeah, there is this important concept of specific energy. Uh, I mean, we are running out of time, and actually, this is our last session, so we don't have next session. So I'll try to cover as many of them as possible, but I'll give you an overlook. So basically, uh, this specific energy is defined as summation of the head, you know, potential head, or depth of the channel, and velocity head, the average velocity of that cross sectional area. We generally neglect the datum because it will be same for all channels since they have very small slopes. And what they do, they write this velocity in terms of, because we know, right, there will be some, if there will be some flow rate, and that will be velocity into cross sectional area. They write cross sectional area as some channel thickness into y, and they convert this expression of E in terms of y. So basically, they make it as a function of y, which will look something like this. And they assume this Q as constant. So the flow rate is not changing with respect to the dimensions and the time. If you do that, what you end up getting is something like Q square by 2g y square b square, and they replace this q square by b square term as some flux, volume flow rate flux type of thing. So basically, they make this E as a cubic function of y, and then they solve it, and you know I mean, there is a famous curve you might have seen in class also, or otherwise also if you have studied open channel flows before this. So this is called as water depth versus specific energy curve. And for a particular Q, which is constant, this there are three roots for this y, right? And one of them is, I think, negative. So only two roots they consider. One root. Okay, 1 second. So one root is nothing but okay. I should have used other color, but anyway. Or maybe I can use some other color. So it looks like it approaches both the roots asymptotically. So what I mean is asymptotic is like it doesn't reach the value, but in infinity it may reach. We don't know. So anyway, the point is there are three roots to this equation, and typically one route turns out to be negative, which is not a practical feasible route, and the remaining two routes, one is basically one route goes like y equal to 0 and another route goes as e equal to y. So that is basically 45-degree line. So this angle is typically 45 degrees. And then if you plot it, you can use any online plotter also. If you plot a cubic function of y, you will get similar asymptotic thing. I have done that. And then there will be a minima, which is called as the critical or minimum specific energy. And for all other things, all other y values, yeah, and this is called as a this is called as a critical y value. Your flow cannot have depth which will be lesser than the critical y value, because then it's impossible flow, because it will have lesser energy than the minimum energy, which is violating the first law of thermodynamics. And then you will have two domains of flow regimes. Here it will be subcritical, and you will have your Froude number less than 1, and in this domain you will have supercritical flow, and your Froude number will be greater than 1. And on this horizontal line, Froude number will be equal to 1, this line. So this is a critical flow. So for any value of y which is greater than yc, you will have, you can have, let's say if you have, let's say this y, this, I mean, for, how should I show this? I don't want to make this figure complicated, but let's say you have some other maybe I'll use some other color. Yeah, so let's say you have some energy state in your flow which is here. So it can have two depths. One can be here, one can be here. So it all depends on which type of flow regime you are operating in. If you are operating in supercritical regime, your y value will be here, and if you are operating in a subcritical regime, your y value will be here. So that's how you have to go about it. So that is there. Yeah, and again they find the minima of this expression. This expression we have, right? So what they do, they take d by dy and equate it to 0. So then you'll get some E mean, and that turns out to be E mean at 3 by 2 y critical, and y critical is nothing but it will be q square b square g power 1 by 3. So this you get the value, and this is commonly used in other cases also. So I can make one question here itself. I can ask you for a rectangular channel. Let's say we have a flow rate. Maybe we can have one question itself only, and similar questions you'll see at a lot of places. For a rectangular channel, you have this flux, not flux, 1 second. Yeah, so basically this q, small q, which is q by b, is nothing but 50 meters square per second. And I can ask what is yc for this channel, critical depth, and what type of flow exists in this channel. So you can use the formula for yc, which is in terms of small q, it will become q square by g power 1 by 3, and it will give you 4.27 meter. You can cross check this answer later. Yeah, and what type of flow exists if your y is 3 meters, so your flow depth is 3 meters. So here you can see, right, here your y is less than yc, so that falls under the regime of supercritical flow, right? So basically, in this figure, in this region I am talking about, here your y is less than yc, so supercritical, and you will have Froude number greater than 1 for such flow. Maybe other dimensions are not given, but it should be, otherwise it's not a supercritical flow. So like that. Yeah. What else? Yeah, then there is this important concept. Oh, we are actually over the time. Give me 5 minutes. I think we can, I mean, I will summarize. Only this hydraulic jump related thing is remaining. But other than that, I think we have covered most of it. So basically, a hydraulic jump, again, is nothing but the analogous physical phenomena as to shock waves in compressible flow. So what happens at one point, your flow, open channel flow will turn supercritical, and if it faces adverse pressure gradient downstreams, uh, I mean, if they're like in at downstream conditions, the conditions are such that it cannot maintain that velocity in supercritical region, so it will undergo a abrupt change in the in the velocity, that is like shock. In the fluid terms, we call it as hydraulic jump, and there is a derivation for it. Nice derivation is there. uh, I'll go over it, but basically in hydraulic jump, supercritical flow turns into subcritical flow, and that is only when hydraulic jump takes place. And mostly the hydraulic jump phenomena is governed by the Froude number existing at the supercritical regime, which is upstream. It is not function of, I mean, surface roughness, Reynolds numbers are there, but primarily Froude number, and it should be greater than 1 or supercritical region upstream, not the downstream. And depending on this upstream Froude number, there are different categories of hydraulic jumps. Some called as standing waves, smooth surface, or weak jump, like that. I think in class also, sir has given you the table. You can refer to it. And depending on the Froude number, if it is a high Froude number or upstream Froude number is high, the dissipation of energy in the hydraulic jump will be higher. So if the Froude number is, let's say, 10, and in another case if the Froude number is 2, so when the Froude number is 10, the more amount of energy, the flow energy will be dissipated in hydraulic jump as compared to the Froude number 2. So like that. So just to give the context, if Froude number is around 2, you will lose around 5 to 15% of your energy, flow energy. But if it is around 9 or 10, you will lose around 70 to 80% of your flow energy. So like that. So basically, high Froude number is results in high energy loss.
So then
And
the depth has to be low, small size in that case. Like if the Froude number has to be more, the depth has to be less, so less than YC.
if you have that flexibility in your hand, you can do that. But many cases it may not be possible. So in that case, you can manipulate V or your flow rate, because velocity is nothing but area into flow rate, right? So let's say you can manipulate area or the y direction flow depth, that is good. Otherwise, you can manipulate the flow velocity also, if possible. So both factors can govern the Froude number upstream. So yeah, then there is one important thing. Sorry to take your more time, but since this is the last class, I'll just skip it.
Carry on, please.
Yeah. So I'm skipping the derivation here, but you can refer to the FM White book and chapter number 10. I think this is third or fourth, seventh edition I have. So basically, we'll solve the last problem and then we'll stop here. But this is important problem. So what they do, they take a control volume and derive this equation. You can find this equation in the FM White book. But for the sake of our discussion, I'll take the starting point from there. So what they do is they write upstream velocity as following function, which is nothing but gy1, and there will be one function like this where this variable is nothing but y2 by y1. So what is y2? Y2 is nothing but the flow depth downstream, and y1 is flow depth upstream. So always, so basically it looks something like this. If you have, let's say, solid surface like this, it will mostly look like this, the hydraulic jump. So always your y1 will be smaller and y2 will be larger. So therefore this parameter will be always greater than 1, assuming this is the flow direction. Yeah, and what they do next is in this equation they introduced upstream Froude number as FR1, which is the formula we all know is G1 Y1, GY1. And if you do that, and you solve for neta, what you get is 2 neta, which is nothing but 2y2 by y1 as minus 1 plus 8 upstream Froude number square power half. So this is the important result. Derivation is there in the book. Unfortunately, I am not able to do it in this time. And from continuity equation, mass continuity, we know that V2 is nothing but V1 Y1 by Y2, because we assume the width of the channel is still same. And yeah, so the important parameter, which is dissipation head loss, it is calculated from mechanical conservation energy equation, which is nothing but, you take the difference of two energies, upstream minus downstream, and the upstream energy will be y1 plus v1 square by 2g, downstream will be y2 plus v2 square by 2g. Now you have v2 expression. This expression relates v2 with v1, so you replace any one of them in this, and y1 and y2 are correlated using this equation. And you further, when you solve it, you get this very famous formula for head loss, which is y2 minus y1 cube divided by 4 y1 y2. So this formula will give you the head loss only based on the y1 and y2 that you can easily calculate in any experiment. Okay. Yeah. So we'll take one problem and we'll stop here because we are running out of time. But I think this is important problem. It will cover almost all the cases. Yeah. So you have a wide channel with this flux, or this is Q by B as 10 meters square per second, and y1 is 1.25 meters. If flow undergoes hydraulic jump, calculate. I mean, there are a lot of, okay, I can write them. Calculate y2, which is the depth downstream, velocity downstream velocity, Froude number downstream, frictional head loss, and then percentage dissipation. I'll tell these terms later, but for now, power dissipated during the jump per unit width. Typically, we talk about unit width because the widths are actually very long and you can just multiply the answer. And important thing is temperature rise during the jump, assuming CP for the water as standard value of 4.2 kilojoule per kg Kelvin. So yeah, we'll solve this quickly. So yeah, we know V1 we can calculate as Q by Y1, because this is for Q by, it's nothing but Q by by1, right? So this is the formula. So 10 by 1.25, so it will give you 8 meter per second. So this is your upstream velocity. Then you can calculate, it has told that it has undergone the hydraulic jump. So it is primarily driven by the upstream Froude number. So that will be V1 by under root G Y1. We have both the values here. Y1 was given, V1 we calculated. And if you put this in the formula, you will get the Froude number which is greater than 1. So hydraulic jump is possible. That is first thing. And this is a weak jump. You can refer to the Froude number table. So this falls under the category of weak jump. So here the energy dissipation will be smaller, basically around 15%. 10 to 15% it should be. We'll check whether we get that or not. To get the Y2 value, we have to use this expression, which is, let's say I mark it with star. We use this equation. So in this equation, basically you have to put upstream Froude number and Y1 value to get the Y2 value. So if you do that, I'm skipping the algebra here because I don't have enough time. So this becomes 2y2 by y1 as that expression. So if you solve it, you should get 5.54. And then you solve for y2, putting y1 as 1.25, which is given. You get 3.46 meter. So this is your downstream height, channel height or flow height. And again, using the continuity equation, you can calculate V2. So that will give you 2.89 meter per second. So downstream velocity is lesser. You can see, right? Upstream velocity was 8, downstream it is less than 3. So that is there. Then you can calculate Froude number downstream, which will be V2 by GY2. I'm skipping the algebra again. This will become 4.96. So see, this is less than 1. So this is subcritical flow. And it has to happen. If hydraulic jump is there, the flow will go from supercritical to subcritical. Here it was, Froude number was 2, so it was supercritical. In some problem, if you see, it is not changing from greater than 1 to less than 1, there is something wrong in that problem. And assuming that they are asking you for hydraulic jump. And for dissipation head loss, we have this formula, which is y2 by minus cube by 4 y1 y2. So you need to put y1 and y2 and you'll get 0.625 meters. So this much head loss is happened in this hydraulic jump. And now it is asking us the percentage dissipation, right? But for that we need to calculate the energy with the flow before the hydraulic jump, which was E1. That will be y1 plus V1 square by 2G. We know all these values. So if you calculate that, you get 4.51 meter. 4.51 meters. So percentage dissipation will be nothing but the head loss divided by the initial energy that the flow had into 100. So that will be in percentage. So that will be nothing but 0.625 into 100 divided by 4.51. So this will be, if you do the calculation, it comes out around 14%. So this is correct, right? Because for weak jump, which we know, right, Froude number is between 2 to 4. So that is a weak jump, and the head loss should be around 10 to 15%. So correct, our calculations are correct only. So this is one check that you can do. Now the power dissipated. So for power in general, you have this formula, which will be rho G Q into HF. I mean, here, Q is per unit width. So you will get, ideally speaking, you will have, the formula is rho G capital Q, which is flow rate, into HF. And this was true for our previous example also, in case of pipe flow in laminar, etc. Right? There also this formula, but in this problem, they have not given us the width. So therefore, we are taking it as a per unit width basis. So therefore, the small q is here. And you can put 1000 for water, 9.81. Q was given as 10 and head loss is 0.625. So if you do that, you should get 61.3 kilowatt per meter, because it is per unit width of the channel. So this is also done, and now the temperature rise. So it's a first law of thermodynamics tells you that whatever is power lost, it will result in the temperature rise, which will be m dot Cp delta T between inlet and outlet. So they are asking about delta T. So for that we need m dot. So m dot is nothing but rho into Q. It will be again in terms of per unit width. So it will be 10 to the power 4 kg per second per meter. You can check the units later. And therefore, we know power dissipated is equal to m dot Cp delta T. So power is 61.3 into 10 to the power 3. Since it's a kilowatt, we convert it into the watt. M dot is 10 to the power 4. Cp is 4.2 into 10 to the power 3, standard value for water, and delta T. So therefore, the delta T comes out to be 0.0015 degrees Celsius. So it is very less. So the point that I wanted to tell you is, even though the hydraulic jump is an energy dissipation process, you will not observe much change in the temperature of the flow after hydraulic jump, because most of the energy is lost in the, that when it turns from supercritical to subcritical, in the dissipation, viscous dissipation, most of the energy is lost and it is carried away with the flow. It won't result in much temperature rise. In case of higher Froude numbers, see here upstream Froude number was around 2.3. So here the delta T is not much, but if it is, let's say, around 10 or more than that, maybe you can get 1 degree Celsius temperature rise also. So you need to consider that also. So with this, I conclude this session. I hope you will be able to solve most of the problems in your assignments. And if you want to further, because it's a very wide field, it's open channel flow. So there are some additional concepts which I am not covering because of the lack of the time. But you can refer to the FM White book. It is a good book for this topic, and you can solve other type of problems also. But most of the things I try to cover. So yeah, so I think this is our last class also. So yeah, thank you everyone who.
Thank you, sir. Thank you very much. You have given a very enlightened to fluid mechanics.
Very intelligent person.
Thank you. Thank you for your compliments. But I think I hope whatever I told during this a limited time helps you or others who watch it later. And yeah, that was the whole point. Anyway, so yeah, this is I think the goodbye. Hopefully we'll meet somewhere.
Thank you so much for that.
Okay. Yeah, Pradeep, you are regular. So thank you for doing that.
Sir. Thank you, sir.
Yeah. Okay. Okay, then we'll close for the day and for this session also. And yeah, thank you everyone, and see you maybe later sometime.
Thank you, sir.
Okay, thank you, sir.
Bye, sir.
Okay. Good night. Good night. I'll close the meeting now. Okay. Thank you. Bye.